50,000. Just take a second to wrap your head around that number. 50,000. That's how many location updates are slamming into Uber's servers every single second. And that's literally just from active drivers out on the road. It is an absolute avalanche of data. You know when you open your app and you're watching those cute little cars crawling along the digital map? You're not just looking at some simple animation. You are actually peering directly into one of the most complex, lightning-fast distributed systems that human beings have ever built.
Okay, let's dive into this. Welcome to The Explainer. Today, we're going to peel back that incredibly simple user interface of the Uber app to uncover the absolute behemoth of a real-time architecture running underneath the hood. We're going to see exactly how a platform makes millions of decisions every single minute. Decisions to connect a rider with a driver, calculate dynamic routes, and, handle sudden massive spikes in traffic, all without dropping a single request. It's kind of mind-blowing.
All right, so here's our blueprint for today. First, we'll look at the magic behind the tap. Second, mapping the world in hexagons. Third, the brain of the operation. Fourth, the math of surge pricing. Fifth, storing millions of trips. And finally, number 6, surviving the chaos. Let's get right to it.
Section 1. The magic behind the tap, from UI simplicity to back-end chaos.
So, as a rider, you just punch in your destination and tap confirm, right? Feels so easy. But that single little tap, it acts like a starting gun. It triggers a massive fan-out of operations across the platform. And to manage all this sheer chaos, the system absolutely relies on a strict ride state machine. Think of it like a very rigid set of rules. A ride has to move precisely from requested to assigned to arriving, started, and finally completed. No skipping steps. Without these super explicit states, the backend would literally just devolve into a mess of impossible bugs. Imagine a race condition where the system tries to process your payment before you even step foot in the car. Yeah, no one wants that.
Moving right along to Section 2, mapping the world in hexagons, the geospatial index.
Now, you might be wondering, when you request a ride, how does Uber actually find you? They obviously can't search the entire globe for your driver. That would be way, way too slow. Instead, they operate kind of like a giant biological nervous system. They categorize where everyone is using an open-source system called H3. H3 is a geodesic discrete global grid system. Now, in plain English, that just means it literally partitions the entire Earth into identifiable hexagonal cells. It totally replaces messy, shifting, arbitrary things like postal codes with standard, mathematically predictable clusters.
And this right here brilliantly illustrates exactly why they went with hexagons over something super simple, like a square grid. Think about a square for a second. If you look at it, the distance from the center to the neighbor directly above it is totally different than the distance to the neighbor on the diagonal corner, right? That inconsistency creates distortion. But with a hexagon, the distance from the center to all neighboring cells is exactly the same. It's uniform. And this uniform distance makes radius calculations and tracking moving objects mathematically simpler and much, much faster. It minimizes what engineers like to call quantization error. It's a total game changer.
Section 3, the brain of the operation, dispatch and matching.
Okay, so to actually match you with a car, Uber uses a system called DISCO, which stands for Dispatch Optimization. Now, the absolute crucial point to understand here is that the nearest driver geographically is not always the best driver. Think about it. What if you're separated by a river or stuck on a weird one-way street? Geographic proximity doesn't mean much then. So DISCO uses complex road network graphs and Dijkstra's search algorithm to calculate the true estimated time of arrival based on actual real-world road conditions. It's not about who's closest as the crow flies, it's about who can physically get you the fastest.
But wait, how do you actually calculate all that for millions of people at the exact same time? Well, Uber built their dispatch system on Node.js to handle some really heavy asynchronous messaging. And to scale that out smoothly across different geographic regions as traffic spikes, they use an open-source tool called RingPop. RingPop relies on what's known as a gossip protocol. Basically, independent servers are constantly chatting or gossiping with each other to discover who's working on what. So if there's a massive sudden spike in traffic, say a crazy unexpected rainstorm hits London, RingPop dynamically balances the workload across the entire server cluster so the system doesn't drop your request.
Oh, and here is a really fascinating engineering hurdle. What happens if two different drivers receive the exact same ride offer, and they both tap accept at the exact same millisecond? It's an awkward race condition, right? To prevent two drivers from showing up for one single rider, DISCO uses atomic locks. This is a failsafe that ensures only the very first successful acceptance actually gets committed to the database. It cleanly and instantly locks out any other attempts. Problem solved.
Section 4. The math of surge pricing. Balancing the market.
Look, I know, nobody loves paying a surge. We've all been there. But from a system design perspective, it is an absolute mathematical necessity. Let's say a massive stadium concert just ended. You suddenly have, I don't know, 500 ride requests pinging from one specific hexagon grid, but there are only 80 drivers currently in that area. That local mismatch triggers the surge multiplier to push prices up. And what this does is twofold. It temporarily reduces rider demand because some people will decide to wait, and it financially incentivizes drivers from neighboring grids to physically drive toward the venue. It literally uses math to physically rebalance the real-world marketplace.
All right, Section 5, storing millions of trips, the database architecture.
Now, what's really interesting here is how they manage all this information. A super common mistake in system design is just assuming one database can do everything. But at this insane scale, no way. You have to strictly separate your workloads into hot data and cold data. Hot data is the stuff that requires extreme low latency. We're talking live driver coordinates updating every 4 seconds. That needs to go into blazing fast in-memory stores like Redis. Cold data, on the other hand, is stuff like completed routes and historical analytics. That doesn't need to be instant, so it gets stored long-term in robust, heavy-duty databases like Hadoop or Cassandra.
And finally, Section 6, surviving the chaos, handling data center failures. This is the ultimate engineering nightmare. What actually happens if a primary back-end data center literally loses power while hundreds of thousands of trips are mid-ride? The solution they came up with is absolutely brilliant. Uber doesn't just copy massive databases over in real time. Instead, they actually use the driver's own smartphone as the failsafe. Seriously? Throughout your trip, the backend is quietly sending tiny encrypted packets called the state digest directly to the driver's phone. If the whole system goes dark, the backup data center boots up, pings all the driver phones, asks for that state digest, and completely reconstructs the entire active marketplace in a matter of seconds. It's honestly genius.
So, what does this all mean? Well, it leaves us with a pretty fascinating final thought. We've just mapped out exactly how a platform coordinates millions of moving humans in real time using hexagonal grids, gossip protocols, and incredibly clever smartphone failsafes. So my question to you is, how are these exact same scalable architectures being adapted right now for the future of logistics? Think about massive food delivery networks, long-haul freight, or even fleets of autonomous vehicles operating totally without human drivers. The foundation we explored today is already powering the logistics of tomorrow. Thank you so much for joining me on this explainer, and hey, keep your curiosity hungry.